a new chapter on solid state. We have already seen the other forms of matter, the gaseous form of matter, the liquid form of matter, and now we are going to see the solid form of matter. The fact that all these three forms of matter can be distinguished by the force of attraction that exists between the molecules, or we can say the constituent particles. Practically, there is no force of attraction that exists between the molecules of a gas, whereas the force of attraction that exists between the molecules of liquid is relatively less. But when it comes to the case of a solid, the force of attraction is fairly high. For example, if we take a crystal of sodium chloride, the sodium ion and the chloride ion are held together by what we call them as electrostatic forces of attraction. Suppose you think of sodium atom, 1 mole of sodium atom. So 1 mole of sodium is bonded to another mole of sodium by means of a type of bonding called metallic bonding. So we'll see it is the force of attraction that distinguishes between a gas and a liquid and a solid. For our study, the solids can be classified into two types. One type of solids we are going to call them as a crystalline solid. The other one we are going to call them as an amorphous solid. Both of them solids in one sense. The main difference between a crystalline solid and an amorphous solid, the crystalline solids have what we are going to call it as a definite shape, or we can say geometry. This is what is going to be very important. The crystalline solids are characterized by a definite shape or geometry, whereas amorphous solids do not have a definite shape or a definite geometry. So an example for an amorphous solid is a glass or plastics like this. So the attraction between these solids, okay, definite. So the major difference between them is crystalline solids are characterized by what we are going to call a sharp melting point. So amorphous solids melt over what you call as the range of temperature. You take any solid, supposing you take solid sodium chloride, it sharply melts at 1400 degrees centigrade. Whereas if you take a glass or rubber, it melts over a range of temperature. That is the major difference between a crystalline solid and an amorphous solid. We are going to concentrate only on the type of solid, what we call them as the crystalline solids. Solids are further classified based on the force of attraction that exists between the constituent particles. One type of solid we are going to call them as an ionic solid. In ionic solids, the force of attraction is mainly electrostatic force of attraction. For example, a crystal of sodium chloride, the sodium ion and the chloride ion are held together by strong electrostatic forces of attraction. So we call this as an example of an ionic solid. Then we think about a covalent solid, where the covalent bonding that makes the constituent particles attract each other. Diamond, for example, carbon atoms are held together by a very strong covalent force of attraction. So this is an example of a covalent solid, diamond, graphite like this. Then we have molecular solids. The covalent solids are also called as the molecular solids. Then we have what we call it as interstitial solids. Solids or interstitial solids. So these are all what we call them as the different types of solid, ionic. These solids we can also say it can be an ionic crystal or a covalent crystal or a molecular crystal, right? Now when you go deeper into this ionic solids or crystals in general, crystals are characterized by three important properties. One important is what we call it as a space lattice. Another important aspect is what we are going to call it as a unit cell. So let us visualize a crystal now. What is a space lattice? Crystals are characterized by constituent particles. The constituent particles can be ions or atoms or molecules. And these atoms or molecules if you try to visualize in space, you will find all these particles are in a fixed positions in different parts in this space. That means, or if you consider all these things apart here, it can go like this in three-dimensional region. Each one we can consider to be a particle. Now the arrangement of this particle in a three-dimensional space, we are going to call it as a space lattice. For example, if you think of a cube like this, so this is one cube is now arranged universally in all 6 faces. That gives you a three-dimensional network, and this is what we call it as a space lattice. And what is the unit cell? This particular portion, that is what we are going to call it as a cube in this case, gets repeated in all the 3 dimensions, three directional region. And this part, the repeating part, we are going to call it as a unit cell. So we can define unit cell as a repeating part of a space lattice of a given solid. So depending upon any space lattice or any unit cell is characterized by 3 important properties. I take for example a cube. Say this is a cube. Easy to draw. Here what we assume that, not assuming, the fact here is this is what you call as the length, and this is all these 3 we are going to call it as the length. They are identical, they have the same length. At this angle, say look at this angle is 90 degrees. Similarly, this angle is 90 degrees. So this is a unit cell characterized by the length it makes and also the angle. The angle we are going to call it as alpha. So here is A is a unit same length, A is equal to A, and the alpha, this is equal to beta, or is equal to, this is an alpha, this is beta, this is gamma. So depending upon this is the angle that the 2 faces can make. Each one we are going to call it as a face here. This is a face, this is a face, this is a face like this. So in a cube we have 1, 2, 3, 4, 5, 6 faces. So each face has got a length. We have got this A. They are identical lengths. The angle that makes is the alpha, beta and gamma. So depending upon A and the alpha, A, B, C or the alpha, we have got different types of unit cells here. So most important of the unit cells we'll have, we are considering only 3 important unit cells. One is called the cubic unit cell, where the axial, the length is alpha, that is equal to beta is equal to gamma, that is this angles becomes 90 degrees, and A is equal to B is equal to C. So this is one type of unit cell we are going to talk about, cubic cell. There are other, based on this, there are 7 types of unit cells. So one is tetrahedral, rhombohedral, like this. We are not concerned about it, we are considering only about the cubic unit cell. So when you think of a cubic unit cell, we are talking about 3 types of cubic unit cell. For example, I draw this. This is a cubic unit cell. Now, what is happening here, you will find there are what we call them as the corners. These are all the points where the constituent particles are present. These are all corners here. So if the particles are present in the corners of a cube, then we are going to call this as a simple cubic unit cell. Okay, now these are all called faces. 1, 2, 3, 4, 5, 6 faces. So it's a simple cubic cell which contains particles only at the corners of the cell. Now, this is the center of a face. This is the center of a face. This is a center like this. There can be 6 faces like this, and in the center of each face you have a particle. We call it as a face-centered cubic unit cell. So in face-centered cubic cell, atom or the constituent particles are present not only on the corners of the cube but also on the face of that. And in between this, if you connect them, there is one thing. This is called the body of the cube. And if the particles are present not only in the corners of the cube as well as in the center of the cube, we are going to call it as a body-centered cubic unit cell. So we have seen 3 simple, these cells we call them a primitive unit cell. So the simple cubic, face-centered cubic and body-centered cubic. Now once we think of the cubic structures, the cells, in a 3-dimensional region, how these unit cells are arranged or how the constituent particles are arranged. Say the arrangement is similar to this. So for example, There is one particle here, one particle here. Let us assume that to be a particle here. So I arrange one of them another like this, one constituent particle, so that each sphere touch each other. There is a one directional arrangement of the constituent particle. Here is one, here is one, here is one, here is one. In this case what happened? You have got a layer. We call this as a layer. And if you look at the layer, you will find there is one hole in between this. That is the hole we are going to call it. There are two ways of arranging. It is something similar to that of the fruit vendor who is arranging the fruits. So I got one fruit here, one fruit here, one fruit, one fruit. This is one row, this is another row, this is another row like this. And how do you arrange the second row? You can arrange the second row in two ways. One, you can keep one above the other, and another one is keep in between the holes between them. So we have got two types of packing. A type of packing, and we can say B type of packing. So what is this A type of packing? There is the first layer, and you have a second layer, and you have the third layer. So the third layer resembles that of the first layer, and the fourth layer resembles that of a second layer. You will get a type of arrangement. We are going to call it as a simple cubic arrangement. So if there is a hole in between them, this is a hole here. So you are going to arrange this another here in between the hole. So this forms the second layer. Then the third layer is like this. So if you try to A, B, C type, the third layer, the fourth layer will resemble the first layer, the third will resemble the second, and this is 1, 2, 3, this is 4, this is 5, the 6, the third layer, the fourth layer resembles the fifth layer resembles the second, and the sixth layer resembles the third. If you try to arrange this like this, you have got ABC type of packing. The ABC type of packing, you can call it as hexagonal close packing or cubic close packing. So the particles are arranged in either in cubic close packing or in hexagonal close packing. The principle of this packing is that maximum available space is occupied by the constituent particle. As I told you, the constituent particle can be atom, molecule or ion. So the maximum available space is we are going to find out. That is called the packing efficiency. So for each particular type of crystal, packing efficiency will be different. The most efficient type of packing is one which occupies more number of spaces. For example, we have a primitive unit cell. Say for a simple cubic system, you will find the packing fraction is found to be 52%. And for an FCC it is 74%, and for a BCC it is 68%. So you will find the most efficient type of phase packing is what we call them as the phase center cubic, and is the least in this kind of simple cubic system. So packing efficiency, very important characteristic of a particular crystal. Okay, then there is a relationship. When we try to packing up the crystals, you will find, for example, if this is one space, this is another, we will assume that all these particles are close to each other, they touch each other Now when you put another layer on this, you will find this is one, this is another, this is another. You will find these are what we call them as the holes, or example we call them as wires in the crystal. This is something similar to, we can see when the fruits are arranged in a fruit vendor. So he has one layer of fruits here, and when he faces another layer, you will find there are some holes here. So he can put the fruit on the holes available on that hole we are going to call them as a void. So if a void is surrounded by 4 surrounding peaks, then this void is going to be called as a tetrahedral void. That is what this is going to be the void. So this is surrounded by 4 what we shall say 4 neighbors. We can put like this. This is one, this is one, okay, this is another, and this is another. Over and above is what? This is 4 neighbors. So this is the tetrahedral void. If there is going to be a 3 surrounding neighbors, we are going to call it a trigonal void. That is, if this is the void, so this is 1, this is another, and this is another. So this is surrounded by 3 surrounding neighbors, so surrounding particles. And another one we call them octahedral void. This is one. That is, this is one, this is two, this is another. Over and above you have another one. So here is the void, 1, 2, 3 particles, and above one, below one, like this. So you will find 6 particles. So this is called as an octahedral void. So a tetrahedral void is one which is surrounded by 4 nearest neighbors, and an octahedral void is one which is surrounded by 6 nearest neighbors. So the number of nearest neighbors of a void, we are going to call them as a coordination number. In other words, in any solid, each particle is surrounded by a fixed number of other particles. This is what we are going to call as a coordination number. If we take sodium chloride crystal, each sodium ion is surrounded by 6 chloride ions. Therefore, coordination number of sodium ion is 6. Like that you will find each tetrahedral void, the coordination number is 4. Because this is a tetrahedral void, this is surrounded by 4 particles. Therefore, the coordination number is 4. For an octahedral void, the coordination number is 6 now. So, based on this we will find this is a very interesting aspect we are now looking into this. I say, for example, this is a void. What is it? This is a void. Now what I have marked here is a trigonal void, let us say like this. A tetrahedral void, if you have one more above, this void we call it as a tetrahedral void. Normally you will find in ionic crystals, anions which are larger in size, they occupy the corners of that space lattice or unit cell. And the cations are smaller in size, they occupy the voids here. So it is the size of this void is able, if the size of the cation is equal to the size of the hole here or the void here, then the cation will just fit in into this void. So you will find that is a ratio of the cation but divided by the ratio of the anion. We are going to call this ratio as a limiting ratio. The limiting ratio is one which decides how many particles can surround a particular void. If it is going to be a tetrahedral void, how many particles can surround a tetrahedral void? If it is going to be an octahedral void, how many particles can surround that particular octahedral void? So the RS ratio is between, this is called the limiting ratio, or we simply call it as a radius ratio. Radius ratio. The radius ratio is between 0.155 to 0.225. The coordination number is 3, and the geometry of that particular molecule is called a plane triangular. Similarly, if the value is between 0.225 to 0.414, the coordination number 4, the geometry is what we are going to call them as a tetrahedral. And if it is going to be 0.414 to 0.732, the coordination number is 6, and the geometry we are going to call them as an octahedral. So, and above this 732 to 1, the coordination number is 8, and we are going to call this as a cubic. So among them, octahedral means this is simply BCC, body centered cubic. So depending upon the coordination number, we can predict what we call them as a geometry or the crystal nature of the unit cell. Alright. Then the density of a solid can also be calculated by using a formula here. The density of a solid is calculated by using this formula, that is, the density is given by Z into M divided by A cube into N into 10 power minus 30, I can say grams per centimeter cube. Here Z is the number of atoms present in a unit cell. I told you the number of atoms can be calculated by finding how many atoms are present in the various lattice. For example, if you take a cubic lattice contains 8 corners. So 8 corners. So each corner is shared by 8 other corners. So each corner contributes 1 by 8 to the total number of the atoms in this particular cell. So like this we can calculate the number of atoms. M is the molecular mass of the substance. A is the length of the cube. N is the Avogadro number. So using all these things you can calculate the density of a unit cell. What do you mean by density of the unit cell? How many atoms can be present in the given unit cell, given volume of the unit cell. So we can calculate this. Then the next aspect of this is what is called the imperfections. Imperfection, or what you are going to call it as a defect in a crystal. So a crystal, you remember, constituent particles are arranged in an orderly fashion in a three-dimensional region in space, which means here is one particle, here is one particle, here is one particle. So like this it goes on in all the three directions. So this is called, now in reality you will find not all crystals have an orderly arrangement of the constituent particles. You will find there are some vacant spaces left. For example, this is one particle, this is one, this is one, this is one, like this. Sometimes there will be a defects in the crystal. This part will be vacant and another crystal here. So this is what we call it as imperfection or defect in the crystal. So we have got two types of important defects we can cover. One we call it as, this defect we are going to call it as stoichiometric defect. One type of defect we call it as a stoichiometric defect, or in general these things come under the classification of what is called point defect, the name given, and one of them is called the deviations that are found in the crystal lattice. We generally call it as a point defect. That is, normally solid particles are arranged in an orderly fashion. There is a different deviation in the arrangement of the constituent particles, then we call that as a point defect. So what are the point defects we talk about as a stoichiometric defect? That is, the number of atoms is A, X and B, Y. What is X and Y? The ratio of A and B in that crystal, let us say like this. So if there are going to be X atoms of A and Y atoms of B, let us say 6 atoms of A and 6 atoms of B. And if there is a defect, if there is one of the atoms are mixing, that is A4 and B4, let us say like this. The actual number of atoms present A4 and B4, that is, ratio remains the same, but you will find the original crystal 2 atoms of A and 2 atoms of B are missing. So this type of defect we are going to call this as a stoichiometric defect. That is, the number of cations and anions are exactly the same ratio as represented by the chemical formula. The defects, they do not disturb the ratio of the cations and anions. So we call this as a stoichiometric defect. The stoichiometric defect is further classified into two types. One we call them as the Schottky defect. SCHOTTY. We call this as a Schottky defect. So what is the nature of the defect? Atoms missing from the lattice point and thus giving a vacancy. Say this is a lattice point. So this is missing now. So this gives you a vacancy in the arrangement of the crystals. This is what we call them as a Schottky defect. Then we have Frenkel. Another defect is called Frenkel defect. The Frenkel defect. The Frenkel defect is something that anion, that is, if this is one atom, this is one atom, this is one atom. So this atom is displaced to the another point here. You are vacant here, but this has gone into the other point. So this is called the Frenkel defect. Or in other words, we will consider this effect first and then come to Frenkel defect. It is called interstitial defect. Interstitial defect. By that we mean, we have an atom here, we have an atom here, we have an atom here. So if an atom or an anion, here is, you have got a hole in between. So if that is, we can say, this is one atom, this is one atom, this is another atom, and you have got a hole here. So in this hole you will find, if it is created, this is called as an interstitial site. So if there is an atom is missing from the interstitial site, we call it as an interstitial defect. Then we have a Frenkel defect. The third type of defect we call a Frenkel defect. This is a combination of the Schottky defect as well as the interstitial defects. Atoms or ions or the lattice points are displaced at an interstitial site, creating a vacancy. Then we have what we call them as F centers. That is, electrons are trapped in an anionic vacancy, we call them as F centers. And we have line and non-stoichiometric defect. Now we'll come to the properties of these. We know they are good electrical conductors. They conduct electric current. So how do we account for the electrical properties of a metal? So there is a theory called electron C theory. What exactly we mean by? We have an atom here, we have an atom. All these atoms, they have low ionization enthalpy. That means they have a loose valence electrons. So these electrons are present somewhere here. They are held together by the nucleus of these atoms. And then therefore, a large number of electrons are present. They are surrounding the metal ions. So the electrons get surrounded by these metal ions. So when you push an electric current through this, the electron keeps moving around. This constitutes the flow of electric current. This is an old theory, what we call them as the electron C model. The modern theory is based on, we know that there are substances which allow electric current to pass through. Those substances we are going to call them as conductors. Then we know there are substances which do not allow the electric current to pass through. We are calling them as non-conductors or insulators. There are substances which conduct partially the electric current at some conditions. We are going to call them as semiconductors now. So any theory that is going to explain why a particular metal conducts electric current, why a particular metal does not conduct electric current, or why this particular substance behaves as a semiconductor. So this is given by a theory called the band theory. What is band theory? We know metals contains atomic orbitals. If you take sodium atom, that is, it has got a 1s1 orbital. So lithium, sodium, they all contain 1 electrons in the valence shell. We know the molecular orbital is the combination of this atomic orbital. We learnt it in the chemical bonding. Atomic orbitals combine to give rise to molecular orbitals. So two atomic orbitals combine and they give rise to two types of atom bonding orbital, bonding molecular orbital and anti-bonding molecular orbital, two types. Similarly, the atomic orbitals of the metal, they combine and then form molecular orbital, and these molecular orbitals are very close to each other. All these bonding molecular orbital, they lie very close together and they just simply form what we are calling as a band. And what happened? There is another type of band here. All these the anti-bonding molecular orbitals or the higher energy level, they forms another thing. This is called another band here. So there is, if you plot energy here, there is a band here which contains an amount of energy. There is a band which contains a higher amount of energy. In between this we have what we call a gap, energy gap now. Electrons can jump from the band to this orbital. This is called a conduction band. That means electrons can jump at the expense of the energy, they jump into the higher band. This higher band we call it, this is called a valence band, and this is called as a conduction band. So electron can jump from the valence band to the conduction band if the energy difference between these two are very low. So the energy difference between them is very low, then the electrons can jump from the valence band to the conduction band, then the substance acts as a conductor. So the criteria for a substance to act as a conductor is the energy difference between this valence band and the conduction band must be low. Supposing the energy difference is very high, supposing this is the valence band and this is the conduction band, the energy difference is so high, then what happens? The electrons cannot jump from that particular band, valence band to this particular band, namely the conduction band. Then we call this as an insulator. So in between this you will find if the energy gap is very small, like this, very small, then this can jump from this, also from this, then this acts as a what we call a semiconductor. So the ability of a substance to behave as a conductor or a semiconductor or an insulator is explained by this theory. Now, then there is another important property, we call it as the magnetic properties here. The magnetic properties depend on the number of unpaired electrons present. The number of unpaired electrons. We have already learnt here in atomic structures, the electron revolving around the nucleus and electron they spin around its own axis. when the electron spin around its own axis, it generates a magnetic field. So if two electrons are present in the atomic orbital, one spinning in this direction, the other spinning in the opposite direction, which creates a magnetic field which oppose each other. That means the particular two electrons present in the opposite spin in a particular orbital will have no net magnetic field, and therefore we call that substance as a diamagnetic. If there is only one unpaired electron, if it spins around its own axis, it generates a magnetic field, and therefore that particular substance will be attracted by another magnet. So then such substances we call them as paramagnetic. So magnetic behavior of these metals are explained by the number of unpaired electrons present in that. Then we have two types of important properties here. One we are going to call it as a piezoelectric. These properties we call them as dielectric properties. Dielectric properties. One such property we are going to call it as piezoelectricity. P-E-E-Z-O. Piezoelectricity. The piezoelectricity means that if you apply a mechanical stress on the crystal, then the crystal starts conducting electric current. So the mechanical stress that produces an electric current, we call it as a piezoelectric current. And another one we call them as the pyroelectricity. That is, the piezoelectric crystals, when preheated, they produce a small current. These crystals on heating will produce a small current, and this is what we call it as a pyroelectricity. Done. Then we have a ferroelectricity, another type of electricity we call them as the ferroelectricity. That is, the dipoles are permanently polarized even in the absence of an electric field. On applying electric field, the direction of polarization changes, and then we have the type of electric current we call them as the ferroelectric current. So with this we will wind up this chapter on solid state, a brief bird's eye view on the solid